today we're going over chapter 12. So chapter 12 is all about chemical bonding. So everything we talked about last time about the periodic table, the valence electrons, we're going to go into more detail about that. So a few things to mention. The homework 11 is due on Thursday. So it'll be due Thursday tomorrow at 11 p.m. This chapter's homework, I will mention when the due date will be. It'll probably be on next Thursday too, because I know next week is the, I think, the midterm. We scheduled the midterm for next week, right? So it'll be next Thursday. So I'll make the homework due on Thursday at 11 p.m. So it's advisable that you try to do it before the midterm so you have enough practice. So the midterm, I will post an announcement about what to expect, like what kind of questions. I'll also post a practice exam. It'll most likely be very similar to what we did on the quiz. So it'll be a mixture of multiple choice, free response, like show your work, fill in the blank. There will be a extensive vocab section and some fill in the blank yourselves. So like for example, sig figs. Then the multiple choice, it will be similar to what you saw on the quiz, but the format may be a little bit different. So you can expect the length to be, you'll have the full period to do it. It'll probably take you the full period, and it'll be from like 4 to 6 pages, just like the practice midterm that I'll be posting. So if you are struggling with anything, please come talk to me. Go to the tutoring at the, I think by Dutton Hall, the tutor especially for this class, or ask questions on Piazza. For the midterm, you are allowed to use both front and back a 3x5 index card. So you can put whatever you want on it. So that's the only other external resource you're allowed to use on the exam, in addition to a calculator. You're allowed to use a calculator. I think I forgot to mention that on the quiz last time, so I apologize for that. But you are allowed to use calculators in this class. I don't expect you to calculate decimals in your head unless it's by a factor of 10, which is pretty straightforward. But that is the policy for the midterm. You can either print the exam like we did the quiz, or I will provide a template that if students don't have a printer, they can view the template a day in advance. So make sure you do it a day in advance so you prepare and you're ready to take the midterm the following day. They can look at the template and copy the template on some pieces of paper so they're ready to take the midterm on the day of, so they don't have to feel like they have to write a template on their answer sheet, because I know that doing that will add time to the test taking experience, and that could take up time of you thinking about the answers to the midterm. So I'll post that template, and I think that's all I wanted to say about the midterm. So let's get started into today's chapter. Today is chapter 12. So we're gonna be talking about chapter 12. This is lecture 13. So in chapter 12, we're talking about chemical bonding. So we're going to be talking about what constitutes chemical bonding and what we can expect when we talk about these things. So first thing we're going to talk about is, we talked about atoms, elements, compounds, but we haven't actually talked about what constitutes those compounds or elements, like what actually forms when we form a chemical compound. So first thing we're going to talk about is cation. So cation, So you can think of them as positively charged ions. So cations are formed when an atom loses one or more electrons. So you could think of it like, cation, cats are. I think there's an expression that cats are positively charged or something like that. I don't know. That's something I remember, like from culture or something. But you can think of that, and the opposite of cation is anion. So anion is like if you think of antagonists, they tend to be the bad guys, so they're negatively charged. So anion. So anion is a negatively charged ions. So we'll encounter both of these types of charges, and it's formed when an atom gains one or more electrons. So an anion is when we gain electrons. So we're gaining more electrons than protons. So now our net charge is negatively charged. And we form a positive charge when we lose electrons, because now we're going to be losing electrons, and now we have more protons than electrons. So now our net charge is going to be positive. So we have a deficiency of electrons. Okay, so those are ions. Let's move on here. Okay, so let's go over this chart here. It'll be very helpful if I'm not paraphrasing it. So here we go. So we tend to form ions that are isoelectronic with neon atoms or a noble gas, because they satisfy the octet rule, and they have full electron valence shells. So the highest sublevel will have 8 electrons. So in this case, nitrogen, it's in the group 5, 15. It has 5 valence electrons, or 7 protons, 7 electrons. So what we have here is what it likes to do. It likes to gain 3 electrons here. So you see here, nitrogen likes to gain 3 electrons. So now it has a filled neon electron configuration of 10 electrons. 2 from the first energy level, the 1s, then 8 from the second energy level, 2s and 2p. So now this electron configuration is the same as neon. So now the nitrogen atom is happy. So anions tend to combine with cations to form stable compounds. So here at the start, we have 7 electrons. We gain 3, so now we have a total of 10. Now, if we go to oxygen, it has 1 more electron than nitrogen. So the net electrons we gain are 2 electrons. And now it has the same configuration as the nitrogen here, the nitride anion. So this is called a nitride anion. We'll talk about the namings in the future. Here, this is called the oxide anion. And see, it has the same electron configuration as the neon gas. 1, 2, 2s2, 2p6. 1s2, 2s2, 2p6. So when we gain 2 electrons, that means we're going to have a 2- charge. Nitrogen has a 3- charge. So if this looks a little bit confusing, I would kind of work through the homework and go through this chart to make sure you understand like what's happening. But essentially, we have nitrogen, we have a certain number of valence electrons. Just look at the group number. The first value will tell you the valence electrons, and you just have to subtract that number from 8, because 8 is the valence shell for the 2 sublevel, the 2 principal energy levels, sorry. And you'll find what the charge will be, and because that represents the number of electrons it will take to achieve the octet for that level. So nitrogen's 3, oxygen's group 6, so it's 2 minus. Fluorine is group 7, so we subtract that from 8, we get 1. So fluoride ion will have a -1 charge here. So it gains 1 electron to become isoelectronic. So isoelectronic means have the same number of electrons and electron configuration of the neon atom. So see here, but mainly you should associate isoelectronic with having the same electron configuration as another element, atom, or ion. So here, all these ions are isoelectronic with each other, and the neon gas, neon noble gas. And here's neon. See here we go to neon. It already has a filled shell, so it already starts with 10 protons and 10 electrons, so it does not do anything. It's happy as it is. And you see here its electron configuration. Okay, so be able to tell the electron configuration, and the number of protons and electrons in the neutral element, anion, double, 2-, and 3-, and you'll be able to determine how many electrons were gained from the neutral atom to form the anion here. Okay, so I will mull over this chart a little bit. The homework will really get you into thinking about this, but you can expect something like this on the exam. Okay, let's go talk about cations now. So just one more thing to mention. See here, the final here all represents the total number of electrons, and you can see that is representative here in the last blue box. 10 electrons, start 10, final 10. Okay. Okay, so these are now cations. So cations, they will also tend to have a change in electrons to form ions, but this time they'll lose the electrons to have a noble gas configuration or the neon configuration. So metals tend to lose electrons because it's easier that way. Metals tend to be electropositive, so they tend to want to give away electrons, and that's why they form compounds of anions. So because the electrons transferred from the metal goes to the non-metal or the anion. In this case, we can see sodium. It's in group 1. We see here that in the neutral element, it has 11 electrons, so it has an excess of 1 electron. So it wants to lose 1 electron to become isoelectronic, 10 electrons with neon, the neon atom here. So the final electron count is 10. And as we go across the periodic table, magnesium is in group 2A or group 2, so it'll lose 2 electrons to form the 2+ cation, and you see in the final state it will go from 12 electrons to 10 electrons, having the same isoelectronic, being an isoelectronic with neon and also the sodium plus ion. So there we go. So you just subtract you just, in this case, you would yeah, right, you would subtract the number of electrons from the group number to find out how many electrons are lost, or no, how many electrons you should have in the ion. But if you just refer to the group number on group 2, it's a metal, so it'll lose 2 electrons. So you get you could say, oh, magnesium is group 2, so it'll form a 2+ ion. So these rules can be tricky to understand. So I recommend studying them and doing the homework. If you want, you could also do flashcards. That's always a good thing too, just to get your kind of your mind thinking about these things. All right, so aluminum, group 3/13. 3, we lose 3 electrons now because that's 3 electrons in the valence shell. So it loses 3 electrons to get formed a aluminum 3+ cation, which is also isoelectronic with neon. So these are all isoelectronic, and they have the same number of electrons in the in the atom itself. Whoops, sorry about that. So we form these ions. So these are the common cations we form with metals. So the group 1 will form +1, group 2, 2+, and group 3, 3+. Okay, so now let's look at these things, the kind of charges we'll see in when we talk about chemical reactions, the typical ions and their charges. Okay, let's go forward. So here are the ions. So here, group 1, all of them will be +1. All of these in group 2, 3+. Sorry, not 3+, 2+. And this group here, all 3+. Aluminum 2. So those are all you have to remember. Transition metals, the ones here in white, they will have variable oxidation. Sorry, not oxidation, charges. So we'll actually have to determine their charges by looking at the anion first in their compounds. But we'll talk more about that later. So we have group, remember group 5. Remember group 5, if you subtract 5 from 8, it's 3. So they want 3 electrons right here. 6 is 2. 6 from 8 is 2. So you want 2 electrons. So these elements want to take 2 electrons. And group 7, they are 1 away from 8. So they want to gain 1 electron to form electron configurations close to neon. And hydrogen here, so hydrogen can be 1+ or 1- depending on what it acts as. So if it acts as an anion, it's -1. So when it's paired with a metal, it's usually -1 charge. However, if you're talking about like an acid like HCl, hydrochloric acid, or hydrofluoric or sulfuric acid, usually H is plus, H+. But we'll talk more about that when we talk about acids and bases, which will be in a future chapter. Okay, so those are the common charges for cations and anions you're expected to know. Remember, noble gases, they have no charges, so they're always neutral. Okay, so now let's go back and let's talk about an active exercise now. Okay. So let's draw a line here. All right, let's talk about the first active exercise for today. So the active exercise, I'm going to ask you to write the electron configuration for the calcium ion. And I also want you to think about with what noble gases are its ions isoelectronic. Okay, so let's talk about this. So think about that table we just went over and find the calcium ion and ask yourself, well, what noble gas is it isoelectronic with? So here is our solution. So hopefully you do this first. So our electron configuration is of calcium. So let's first start with calcium. What is its electron configuration? So remember, it's in the fourth row. So calcium's in the fourth period. So we list up all the way up to the the 4s sublevel. So we're going to write 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. Remember, we do not go to the 3D level because the D block doesn't start until we reach the n equals 4 level. Okay, so that's the energy configuration for calcium itself. Now we need to figure out the calcium ion. So the calcium ion is, if we go back to our table in the previous slide, we saw that it's in group 2A/2. So it's going to have, it's a metal, so it's going to lose electrons. So we're going to have a charge of 2+. Sorry, guys, it's just a smudge. Okay, whoops. All right, calcium ion. Let's pull my these. So the calcium ion is Ca2+. So now when it's Ca2+, we're just going to remove 2 electrons from the highest energy level. So we're going to remove them from the 4s2 because the valence electrons, they're the highest occupied energy level. And in this case, it's the 4s2. And we only remove 2 electrons. So all those electrons from the 4s get taken out. So the electron configuration. Of Ca2+ is 1s2, 2s2, 2p6, and now 3s2, 3p6. So see here that we have removed the 4s2, so they're now taken away. Okay. So let's count these electrons: 2, 4, 10, 8. So that's 18 electrons. The calcium ion has 18 electrons, which makes it isoelectronic. So if we look at what has 18 electrons, the noble gas is argon. So argon, colorless gas, is present in our atmosphere. So it has isoelectronic with argon or Ar. With argon, Ar, C equals 18. Okay. So that is how you would do this problem. This is a fair question to expect on like an exam or something. So pretty routine, but work through that example. If you are having problems doing that, let me know or talk to your classmates. Um, someone is bound to understand and help each other. That's one way to learn the material. Always also to reinforce it to teach someone else who doesn't understand. So it makes you as both sides benefit. Okay, so that is that active exercise. Let's move forward. Okay, so now we're going to switch gears. So now let's talk about ionic compounds. So ionic compounds. What are ionic compounds? Okay, so compounds of the ionic type, they're composed of ions, not neutral elements. So ions are held by ionic bonds. So basically, electrostatic attractions by positive and negative ions. So those are ionic bonds. So an ionic bond they are a chemical bond arising from the attraction so the attraction forces, or we could just say attractive forces oppositely 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 charged particles. Sorry, I can't speak today. In this case, we say ions. Ions in an ionic compound. So the thing about ionic compounds, they're also called salts. You know, like sodium chloride. You look at, for instance, sodium chloride, it's actually a solid. So at room temperature, these compounds are very, very stable and they form very strong bonds. So they're usually almost always solids at room temperature. So certain kinds of rocks, they're made of these ionic compounds and they appear solid. So nearly all ionic compounds are solids at room. Sorry, not room temperatures. Just say normal temperatures. At normal temperature and pressures. And one last thing about ionic compounds. So these solids, they tend to form a very, very patterned geometric structure, and we call that a crystal lattice. So they're very nicely arranged in a lattice structure, and it has to do with these ionic bonds forming this repeating structure in a crystal lattice. So the solid has a definite geometric structure called a crystal lattice. So you can expect this for all ionic compounds. Okay. So another thing about ionic compounds is, so for ionic compounds, the combination of charges are always in such a number that overall the compound is neutral. I'll give an example of this. Combination of charges are always in such numbers that the ionic compound such numbers that the ionic compound is electrically neutral. So for example, say I have sodium chloride. So sodium chloride, there's a one sodium ion and one chloride ion. So remember, sodium is in the first row or first column, so it has a sodium plus sign. And then chloride is in group 7 of the halogens, so it has a -1 charge. So see, they combine here to form sodium chloride, where their charges are attracted to each other and they cancel out. If we had something like magnesium bromide is MgBr2. Mg, remember, is in column 2, so Mg2 plus, and we have Br minus. Br is a halogen in the same group as chlorine, so we have -1 charge. So the compound formula is MgBr2 because we need 2 bromine ions to cancel out the charge for magnesium, and so this is how its structure is arranged in the crystal lattice. 1 magnesium coordinated or bonded or kind of in the vicinity of 2 other bromine atoms to form that crystal lattice structure or that geometric structure in the solid. Okay, so that is the combination of charges. So next, the bonds in an ionic crystal are very strong, as we have pointed out. So, which is why nearly all ionic compounds are solids at room temperature. So the strong ionic bonds is a consequence of this, and it also explains why ionic compounds, they tend to have very high melting points. So it's not very easy to melt them. Are solids at room temperature. Okay, here we go. So let's talk about a little bit about their properties. So liquid ionic compounds. So those are called ionic liquids. So they're basically liquid forms of ionic compounds. So they're not under solid state. And water solutions of ionic compounds. They are good conductors. So when these things are dissolved in waters, they can form electrical charge and in water, so they are good conductors in solution. All right. Okay. So let's give an example of what these reactions look like. So let's look at this picture here. So here's the reaction of sodium chlorine. So sodium metal will burn bright with a bright yellow flame. So see how it's burning here, reaction with chlorine gas. So that reaction causes a lot of heat to be expelled, indicating that very strong bonds are forming. So here, and the reason it appears yellow is because sodium has it has energy levels in it, and remember when we talk about energy levels, if we eject an electron, it could jump, it could gain energy and get removed. In this case, because chlorine produces, the reaction with chlorine produces enough energy for it to steal its electron and form sodium chloride. So this color is a result of that energy, of that photon of light having a wavelength that's in the visible region here. So that's why it appears yellow. So it's a color change because you start with a sodium metal and chlorine gas, not really colored, but now here you see this bright yellow flame indicating that a chemical reaction has taken place. So that is pretty cool here. This is let's see here at the bottom, that's where the energy dies down and you can see the smoke it gives off here. Okay, let's move on. Let's talk about what's happening on the molecular level, looking at this next slide here. Okay. So we're just going to talk about schematically what happens on the molecular level, or the atomic level, sorry. So here you have a sodium atom, and here's a chlorine atom of chlorine gas. So now chlorine, you know, it has 17 electrons, so it's missing one electron to get 18 in the dirt energy level, the full shell. And here, sodium has one extra electron away from the filled complete filled noble gas configuration for neon. Right, for the neon atom. In this case, chlorine wants the electron configuration for argon. Remember, argon is 18. Neon is noble gas for 10 electrons. So here, sodium wants to transfer its electron to chlorine. So chlorine is happy as this argon electron configuration, and sodium is happy as the neon electron configuration. So these two will combine and form this crystal structure, the salt. See here is pure salt in a very solid, very crystal-like nature. And here's the model of the crystal lattice. And you see here that each sodium atom is going to be, there's going to be a chloride ion. So not the sodium atom, sorry, the sodium ion is bounded to the chlorine anion in this lattice. So it has a repeating structure: sodium, chlorine, sodium, ion, chloride ion, anion, sodium, chloride, etc. See how it repeats in that structure, and this unit is what repeats throughout the whole solid. So it's very definitive, very geometric, and very patterned. And you see here, sodium is the gray spheres, chloride is the green spheres. So they will attract each other to form this very strong crystal lattice, and that's why it explains this very nice solid shape and why it's very hard to break because of these ionic or electrostatic attraction forces here. Okay, let's go on here. So here is another depiction of the crystal lattice. The lines are just to show the spacings or the relative positions of sodium chloride ion. So see here, it has a repeating pattern, and here is its space filling model. Show how they are tightly packed together, so they have very strong attractive forces between the ions. And you see in a 3D shape, all these ions are going to be surrounded by multiple of the sodium ions. So all those attractive forces give rise to the strengths of the ionic solid. And you see chloride is going to be surrounded by also a chloride ion in the middle will also be surrounded by 6 positive sodium ions. So it goes for sodium and chloride, since they're in a 1-to-1 ratio, they'll be surrounded by each other a total of 6 times, because there's 6 faces for, in a cubic structure. Okay. So let's go on here. So let's talk about now. We're going to talk next about how these are good conductors. Okay. So if you do a little experiment here, you put like a bulb and connect it. We could test the electrical conductivity of an ionic solution. So if we were to put a solution here of water and say salt, something that produces ions in solution, you'll get electric current, and you can actually power things, because these form solutions that are very good conductors. It conducts electric current, and one of the great properties for ions, ionic solids, and materials in general. Okay. All right, so now let's switch gears. We're going to talk. So that was ionic bonds. So hopefully that made sense. You have ions. They form very strong crystal lattice structures. They're very organized, and they're solid. They form very strong bonds by attractive forces of opposite charges, and they are good conductors in the liquid state. So in water, or as a liquid itself, but usually it's water dissolved in water. Okay, and it can conduct electric current. So now let's talk about the other type of bond that we currently, or that we normally encounter in chemistry, and that's called the covalent bond. So let's talk about that. So as you recall, last chapter, that ionic metals usually form ionic bonds with nonmetals, and in this case, nonmetals, they form ionic bonds with metals, and they form covalent bonds with other nonmetals. So we're going to talk about that now. So here's a covalent bond. So they are chemical bonds, or chemical bond. So chemical bond between 2 or more. Between 2 or more atoms that share a pair of electrons. So if you call them ionic bonds, electrons are transferred, or they're stolen by the anion or nonmetal, and the metal donates the electrons. In this case, they instead of transferring, they share their electrons. So they each participate an electron from both species, both elements of a bond, or atoms of a bond. So they share their electrons instead of it being transferred. So you get no ions forming in this case. So it's covalent. You kind of think of like cosine. You share the responsibility of something. In this case, we're sharing the electrons of a chemical bond between 2 atoms. So here, bond is permanent until broken by some chemical change. Okay, so let's talk about molecular compounds. So molecular compound, fundamental. So we have fundamental particles, are molecules, rather than ions. So in covalent bonds, they're called, we don't call them ions, we call them molecules rather than ions. Okay, so what are molecules? I think we went over this before, but let's go over it again. Molecules, let's highlight this. So smallest unit particle of a pure substance. That can exist independently and possess the identity of a substance. So we tend to say they're molecules, that they're more than one atoms instead of a pure element, a pure molecule. So that's the smallest unit particle of a pure substance. For example, water molecule, hydrogen molecule, which we'll talk about in the next sentence. So those are the smallest unit particle of a pure substance that can, as it says here, that can exist and possess the identity of that said substance. And we can actually, we know what it is in the real world. Okay. So the covalent bond, that's how we they are what we refer to as molecule. The bond in molecules in between two atoms that form molecules. That's what a covalent bond is. That's the molecule itself we refer to as or if we're just talking about the molecule in general and not its individual units, we refer to the molecular compound as a whole, and we could represent it using covalent bonds right here, like so. So representation of the formation of a molecule of H2. So this is hydrogen gas. So and there's a number of elements that have this diatomic nature to it. So they'll be composed of the same element with a 2 subscript. So hydrogen gas is one of them. You may know O2, nitrogen gas N2, fluorine gas F2, chlorine gas Cl2, iodine is actually a solid, but it's I2. And then there's bromine, which is a liquid, Br2. And I believe those are all of them. So we're using Lewis symbols. Okay, so for example, we have two hydrogen atoms combining like so. There's the symbols. They combine to form. So when we write a chemical bond, we can say the two electrons come together and pair. because a bond is a pair of electrons. So we say it comes together and pair its electron with each other to form an H dot dot H molecule. Or you could write it as a line like so, symbolizing that the electrons are attracting each other, the nucleus of the hydrogen atoms, to each other, creating that bond or attractive force between the two atoms. So either convention is fine. The ones we're most common with is the second one, the line representation of a bond, but either notation is fine. Students learned the concept of a bond in different ways, so they're both correct. Okay, let me just get a drink of water. All right, let's go. Okay, hold on. Let me get some here. Okay, so all right, so let's just go back to another slide and talk about conductivity. So so if we were to test something like table sugar or something like water, and try to do a conductivity test for lighting, say, a light bulb, we wouldn't be able to detect electricity because even though water is composed of very, very small amounts of uh, protons, H plus and OH minus, and ions, excuse me, sorry. Um, it will not conduct electricity because those ion concentrations are so small at like room temperature. Table sugar will dissolve in water, but unfortunately, it does not produce ions because table sugar is a molecular compound, so it has covalent bonds, so it does not produce any ions. So it will fail to conduct and light the bulb. Um, as we can see on the left, pure water, we just say it has no ions at all because um, water tends to be a molecular compound and not ionic. So we say it does not produce ions. However, remember when we saw the other example, when we put a solution of sodium chloride, now there's going to be a flux of ions in solution. And so it does contain water, and the ions are mixed in solution here, and that will conduct electricity and light, complete the circuit to between these two electrodes here, and that will light the light bulb. So like when people like in like movies and stuff, they draw like toasters and stuff into like a bathtub. Technically speaking, it shouldn't be able to conduct electricity because water has no ions. But you know, so on TV, don't and movies don't always believe what you see. That's just one of my debunking things. I will not expect it to conduct electricity. Have I tried it? No, please do not try that. It's just one of those things I thought I'd debunk for you. So, and to conduct electricity, to create a circuit in solution, you need to have some ions in there. You just can't have pure water. It's not a conductor. Water is not a conductor of electricity by itself. Okay, so that's my take on that. Okay, let's go on here. Move on. Okay. Okay, let's go to the next one. Okay, so now we're going to talk a little bit more about the covalent bond here. So the electron cloud or charge density formed. formed by the two two electrons is concentrated in the region between the two nuclei. So that's the manifestation of the chemical bond, that the electron density is between the two nuclei. And so that bond region, as we shown earlier here, that's where the electron density is going to be associated between the two atoms. Traded in the region between so we also call this the interatomic axis, because that's where a bond, the electron density or charge density, electron cloud is going to be concentrated, because we formed a chemical bond. So now the electrons are only attracted to the nucleus on one atom, they're actually attracted to both of the nuclei on the atoms that compose the bond, the chemical bond. Okay, so another thing we have to talk about is, so we call this the density, charge density, or electron cloud, because that's where the electrons they kind of form one unit to kind of represent that concept. So next, let's talk about orbital overlap. So the thing about orbitals, they can be very vague. So talking about these like things like chemical bonding can seem abstract, but hopefully I haven't lost anyone in thought about that. So overall orbital overlap, so something you should also consider. Orbital overlap is the merging of two atomic orbitals and their associated electrons to create a covalent bond. So it's where we take two orbitals and we kind of, like join them together. They overlap. So now the orbitals, they form something new that represents a chemical bond. So those electrons that are in those orbitals now are kind of paired, and they represent the whole compound. So that's a covalent bond. So there's also one more term we should think about. It's called the half-filled orbital. So the half-filled orbital, when an orbital has a single electron, so when an orbital has a single electron, it can't participate in bonding if it's not in covalent bonding, at least. If it's not in covalent, if it's not singly occupied, no covalent bonds can take place, because there's no space to accommodate an extra electron from another atom to form a bond. So it has to be half filled. So when an orbital has a single electron and is capable of forming covalent bonds by sharing with other atoms. So just like in the hydrogen example up here, they have half-filled orbitals. So the 1s is half-filled. So they can combine with each other by sharing those electrons to form a covalent bond on the right there. Okay, so that is covalent bonds. So now let's look at how that looks like on the on a like a schematic. Okay, so so here so let's share now to another picture. So here is the formation of hydrogen molecule, the reaction we just went over, in fact. So here we have hydrogen molecules, and we say that electron, maybe the electron is here. The instantaneous position of the 1s electron in each separate atom at the same instant before it's being formed. So, you know, there's a probability of finding the electron here or at different parts of the molecule. So we say maybe it's here and maybe it's here. So they combine here, they share their one electron on each atom, and now they form overlap of orbitals where now these electrons are being attracted to both nuclei of the two hydrogen atoms. So this electron pair is going to be shared by this atom. So this nuclei here and this nuclei here. So this forms the H2 molecule. So takeaways here that they have a singly occupied electron, a singly orbital that has one electron on each atom. They will before the molecules form, they'll look like two atoms, and when they come together, they'll form an electron pair that is shared by both atoms. So do not worry about what the orbital, like what the picture should look like. Just know that this is the H2 molecule here. Okay. Let's go back now. We're going to talk next about Lewis diagrams. Okay, so Lewis diagrams. Lewis diagram. So it's a diagram. Obviously a diagram, right? But it's basically a visual representation of something. Diagram representing can't speak today, the valence electrons and covalent bonds in an atomic and covalent bonds, the valence electrons and covalent bonds in an atomic or molecular species. So next we say a half-filled, a half-filled 2p orbital from one, say we have the fluorine atom from one F atom overlaps a half filled two p orbital from the other F atom. So it doesn't have to be the same atom. It could be a different atom. But just in this example, we're going to talk about the same atom in the F2 molecule or the diatomic. The F2 diatomic element or molecule in this case. So the other F atom. So here we have, remember, fluorine is in the halogen, so it has 7 valence electrons. So it wants to gain 1 electron to get to the noble gas configuration. So we draw the electrons around the fluorine atom like so. And then we get when we form the F2 molecule, we should always count around each fluorine atom 8 valence electrons. So an octet of an electron. So each element here has 8 electrons on the right for each fluorine atom. So that's good. So then we could say, we could write show the chemical bond as a line, or we can just write the fluorine atoms as FF and like so. So any 3 of those notations is okay with me at this level. So let's move on here. So that's the Lewis diagram, electron dots. So don't for on each side of the letter F, don't put more than 2 electrons. So you can only put 2. That's why we space them around the element there. Okay. Some more terms for covalent bonds. So let's look at them. So covalent bond continued. So let's talk about lone pair. Some of you may have heard of this term before. Lone pair is a pair of electrons. Pair of electrons. Let's say valence electrons. Valence electrons in the molecule. In a molecule that are not used for bonding. So for example, in my fluorine example, the fluorine here, in my compound F2, we see that there's 3 lone pairs on each fluorine atom because they're not being used in bonding, right? So 1, 2, 3, we see that we have each a pair of lone pairs right there. So those are what we call lone pair of electrons. As you move on into your chemistry education, you'll learn more things about what lone pairs are used for. Okay, so now let's talk about the famous octet rule. So octet rule, atoms tend to form stable bonds by sharing or transferring. So in this case, sharing is for covalent bonds, transferring or an other atom stealing them. That's called transferring. That's ionic bonds. Transferring electrons until the atom is surrounded by a total of 8 electrons. Let's just write it out. So remember, valence electrons, we only count the S and the P sublevels because usually the D and F sublevels, they're usually a level down before the principal energy level. So the total max you can have is 8, and that's why we call it the octet rule. Some elements don't form octets, but we're not going to talk about that. Like hydrogen, it can only have 2 electrons in its valence shell, but we're not going to talk too much about that. I don't think so. Okay, so let's check the time. A little bit less than 10 minutes. Okay, guys. So, okay, everyone. That's sorry. Try not to say the former term without a habit, unfortunately. Okay, so now let's talk about now we're going to talk about 2 classes of of covalent bonds. Polar is a term I'm going to use in a minute. So let's talk about those 2 types of bonds. So now we have 2 classifications of covalent bonds. Is it polar or is it nonpolar? Maybe just leave it singular. So now let's talk about polar. So polar, think of polar like if something's polarized, something is uneven. Like like in politics, like certain groups of people are polarized on certain topics, so they have a bias or they greatly support one side over the other. You can think of it here, polar, meaning that there's a very there's not an even distribution of electrons. So in the molecule, one side of the molecule, one atom is going to hog or kind of want to attract the electrons more than the other atom. That's what we mean by polar covalent. So polar, bonding electrons are shared unequally. Like, if you want to share a piece of pie, you probably want to take the larger half. So you want more than what the other person wants to get. So polar, unequal. So we characterize this by extreme charge density, density shift results in the formation of an ionic bond. So polar covalent is kind of on that same scale as ionic. The more polar covalent you get in the type of bond, the more you're trending towards ionic, because that's a complete separation of charge. So one atom like the charge so much, it's going to become an anion, and the other atom loses the electrons and becomes a cation. So polar covalent is kind of in the middle of the extreme of pure covalent and pure ionic in bond. So it's always most covalent compounds is always somewhere in the middle. Okay, negative. So that's an ionic bond. So it has a negative pole. Bonding electrons. Bonding electrons are closer to the atom. Having higher electronegativity. So electronegativity, we're going to talk about what that means. But basically, it means that an element, depending on what element you're talking about, some elements of the periodic table will tend to have a higher attraction to pull electrons to itself when it's in the bond. So certain elements do have that, and mostly non-metals tend to have higher electronegativities than metals. So there's a trend on the periodic table. We'll go over that, I think, in a few slides or soon. Okay, so positive pole is just the opposite. So remember, if you're polar, have positive and negative poles, just like the Earth has the south and the North Pole. Okay, positive pole. So a positive pole is bonding electrons are seldom close. So at the positive pole, you don't have much electrons being kind of close by because they're being attracted to the negative pole of the more attractive elements. So bond electrons, they're not going to be very close to that pole at all, or seldom close. And seldom is just another word for like rarely or not often. So just keep that in mind. So let's highlight a few things here. Polar. So now let's talk. So this will be the last thing that we talk about. So non-polar. We only have like 2 minutes left. So non-polar bonding electrons. Electrons shared equally between 2 nuclei. So in this case, there is no preference for where the electrons are attracted to. So we say that the sharing is equal. So the charge density So we say the charge density is centered in the region between the bonded atoms. So that's more like the definition of a covalent bond. So the charge density is centered in the region between the 2 nuclei of the bond atoms, or between the bonded atoms, as we mentioned before. So lastly, a bond between identical atoms For example, the F2 molecule and the H2 molecule we talked about. All right, so this will be the last thing we cover. Between identical atoms is always nonpolar. So those examples between hydrogen and fluorine, they're the same atoms. So a bond between them will always be nonpolar because they have the same electronegativity. So there's no preference for which one hogs the electrons. Okay, so everyone, that is it for today and this week. Most likely we will finish this chapter next time, and I think that will be it that we'll cover. That will so that will be the extent of what we will cover on the midterm exam. Whatever I go over in the next chapter on Tuesday, I will most likely not emphasize it on the exam, but I wouldn't put it out there. So whatever we do cover, just review the notes that I talk about, and do not worry extensively about covering the homework for that chapter. Just worry about what I cover in the lecture, and I highly doubt that will be on it, but I can't say that for certain. So that is it. I hope everyone, I don't know about you, but here in the Bay Area, it's getting pretty chilly. So if it is getting colder up there, stay warm, stay safe, have a great weekend. And I would start studying now. So if you're not, reviewing the homework is one of the best ways to prepare, but also after you review the homework, maybe do some book problems if you are not feeling comfortable enough with the material, or asking questions on Piazza, forming study groups. I think there's some study groups being formed within the class, so that's a good thing to do. And always go to tutoring if you need it. If you have questions about the quiz, always going over that. You can maybe expect something similar on the exam, maybe a multiple choice question again, or show your work. But that is also a good way to review. Reviewing your notes as well is very good. Having notes that are organized, that present the information well, that is always a good thing to do in addition. But yeah, good luck studying, and I hope you all do well. And but do attend office hours if you are struggling. Remember, I made that announcement. If you attend office hours, if you do answer questions on Piazza, if students ask questions, you help them answer. I'm willing to assign, participation as extra credit at the end of the quarter. So I'm always encouraging people to come to office hours, especially office hours, because it shows me that you're taking this seriously in your education, and you want to learn. So, but anyway, guys, have a great weekend, and I'll see you on Tuesday. All right, bye.